Now we talk about a very interesting topic which is called diversity. So if we look back into our lectures, we see that the input-output model for uh, binary communication was given as y is equal to hx plus w, where h is given by this distribution and omega or w distribution is given by these values. And we also found out that the event of deep fade has this statistic where h square is smaller than 1 over SNR. Now, we see that reception only relies on a single path h. Now, there is a significant probability of h square that it would be less than 1 over SNR. This h could be in deep fade. Whenever you send the symbol at the event of deep fade, there is a low probability of detection, so it's a troubled communication because the communication reliability would be very low. Now, what to do with this? How to cope up with this situation? One method is to increase the number of paths intentionally. This in turn means that we are trying to increase diversity. By diversity here we means that we send our symbols on self-created independent paths. So, what is the benefit of creating these paths? If one path is in deep fade, there is a significant probability that other paths are not in deep fade. So these other paths can compensate. We will see that we can achieve diversity in a number of mechanisms or ways. Diversity can be achieved with the help of time notion, with the space notion, and by varying frequencies of the transmitted signal. The outlook of the coming lectures on diversity is such. First, we will go into the detail of time diversity. In time diversity, we will be going through coding and interleaving, and we will find out a performance of time diverse systems. We then extend the time diversity case into repetition coding and another version of repetition coding called rotation coding, which utilizes degrees of freedom in a better way. Then we move forward to the space or antenna diversity, in which we would consider receive diversity, in which we have multiple receive antennas, transmit diversity with multiple transmit antennas, and the combination of both receive diversity and transmit diversity, and come up with special codes called space-time codes. At last, we will consider frequency diversity, which is used for inter-symbol interference mitigation, time domain equalization, and direct sequence spread spectrum. And at the end of the frequency diversity, we would have the OFDM. We will discuss in detail OFDM, which uses the frequency diversity scenario. Time diversity. Time diversity can be achieved by repetition coding and interleaving. It's a very simple idea. Repeat the symbols that you are transmitting over L time slots. Now L here should not be confused with the notation of L, which represented the number of taps in earlier lectures. What we do is we encode the information symbol B into code words. Now the code word here is given as a vector X, which is defined as the concatenation of different scalars. and the scalars, all scalar values are the same. So what we are doing here is basically taking in the symbol B and putting out multiple entities of B or repeating B. So the input-output model of such system would be YL is equal to HL XL plus WL, where H is a scalar and L is equal to 1 to 2L. Now, as long as channels HL given by L is equal to 1 to L are not all in deep fade, there is a good probability that we can decode the symbol. Interleaving. Why we do interleaving? So channels within coherence time are highly correlated. Diversity would be obtained if we interleave the code words across multiple coherence time periods. This is well explained in the figure coming ahead. The top figure is representing the different channel conditions have different coherence intervals. So this is the coherent intervals in which the channel remains almost correlated. Another coherence interval or called coherence time, channel remains the same. This is the coherence interval, channel remains the same, and that's the coherence interval that remains the same. Now L here is taken as 4, so it means that you are sending your repeated signals or different code words on totally independent channels. But if you see here, this channel is a very low scalar value of HL. So this probably could be in deep fade. So if you are not doing interleaving and you are just repeatedly sending your symbols, which is represented by L is equal to 4, so the code word x2 here, would be basically completely lost. But if we do interleaving, so if one channel state is in deep fade, then all the code words can be extracted from the previous symbols or the symbols coming later. That is H1, H2, H3 and H4. So what we are doing here is basically increasing the diversity. If you mathematically analyze this repetition coding, the first thing we have to do is to convert this system into equivalent vector channel. The original channel is given by such. When we do interleaving, we have done it in this way. HL is IIDs with complex normal distribution, mean 0 and variance 1. Repetition coding means that every x L would be equal to x for L is equal to 1 to L. The vector channel will be given by vector y is equal to vector h into x plus w. All these vectors are given here. If we analyze the error probability under BPSK, after the projection we get a scalar equivalent channel. So y hat would be equal to, y tilde would be equal to norm of this x plus y tilde. X is equal to plus minus a and w would be equal to complex normal distribution with mean 0 and sigma square. The probability of error would be given by expected value of this Q function, that is approximately equal to this combination of 2L minus 1 into 1 over 4 SNR to the power L. What is the probability of deep fade here? As we earlier found the probability of deep fade, when which h square, where h was scalar, was smaller or equal to SNR minus 1. In this case, we have as h a vector, so we will take the norm of h square less than SNR to the power minus 1 as the deep fade event. So what is this h norm of square? This is equal to sum of L is equal to 1 to L, HL square. Now what is HL square? And the sum of these HL squares, what is the distribution? I mean, this distribution is basically sum of IID exponential random variable with an argument 1. Each HL is exponentially distributed, or each HL square is exponentially distributed. So we have to find the distribution of the sum of such all HL squares. So the density of this HL square is given by fx is equal to 1 over L minus 1 factorial into x to the power L minus 1 e to the power minus x. It is a function of, again, e to the power minus x, but with a weighting factor which is given by 1 over L minus 1 factorial x to the power L minus 1. This distribution is called chi-square distribution or chi-square distribution, which has 2 multiplied by L degrees of freedom. So the probability of deep fade can be found out if we have found fx. First we need to approximate this. Fx can be approximated as such if the value of x is in the range of 0 and 1, which in our case it is true because we have normalized the variance of the Rayleigh fading edge close to 1. So probability of h square less than SNR minus 1 would be approximately equal to 1 over L minus 1 x to the power L minus 1 and integrate it over 0 to SNR minus 1. That would be equal to 1 over n factorial into 1 over SNR to the power L. So this is the curves for the chi-square distributed PDF, probably h square SNR minus 1. So as L increases, this curve goes down in the values of the powers, and it is spread over different values of x. If we do a comparison of probabilities of deep fade, we see that without coding and interleaving, simple communication would be SNR minus 1. So with coding and interleaving, it is proportional to SNR to the power minus L. So the diversity increases from 1 to L. The curve for L is equal to 1 is a simple case as we have done before, and if we increase the diversity branches or repeat the interleaving and coding, L is equal to 5, we have very less error probability for the same SNR.